All right, good morning everybody and welcome. Thank you all for coming to my talk. So my name is Jason Staggs. I am a security researcher from the University of Tulsa in Tulsa, Oklahoma. And this morning I'm going to be sharing some of the findings of a research study that we've been conducting over the past couple of years into an investigation to see how resilient wind farm control networks are to cyber attack, all right? And I think the ultimate goal of this talk is to sort of give you guys a taste as to what the current state of security is in terms of wind farm control networks, and also be able to introduce you guys to how wind farms work from a networking perspective. And lastly, talk about some of the attack tools that we've developed in order to target wind turbines. But real quickly before we get started, just out of curiosity, how many people in the audience actually work in the energy industry? Okay, cool. Then of those, how many of you guys work with renewable power sources? Particularly wind, hydro, solar, et cetera. Awesome. Do we happen to have any wind farm vendors in the audience by chance? Don't be shy now. All right. All right, we're going to have fun this morning. All right, so a little bit about me. Again, I'm a security researcher. I love my job. I'm interested in all things security. I have particularly strong interests in embedded and control systems, network security. Went to graduate school at the University of Tulsa. Gave a talk a couple of years ago called How to Hack Your Mini Cooper at DEF CON. I really enjoy trying to break things. In fact, most of the time I try to provide people with ideas or solutions on how to fix the things that I broke. And sometimes people are willing to listen to these ideas with open arms, okay? Unfortunately, sometimes people, quite frankly, just don't want to listen. And when people don't want to listen, bad things tend to happen. All right, so a little FYI before we get rolling here. So all the affected parties have been properly notified about the security issues that we're going to talk about in this presentation, okay? I am not a power grid engineer, okay? Let me repeat that again for the record. I am not a power grid engineer. I am merely a computer scientist who enjoys flipping bits and constructing packets, okay? And then lastly, please, for the love of God, do not try this stuff at home. Meaning, don't walk up to a turbine out in the middle of a field somewhere and try this stuff because A, you probably won't get caught, but you just shouldn't do it. And then B, this stuff can be very, very dangerous if you don't know what you're doing. So, why in the world would anybody want to hack a wind farm of all things? Well, let me explain. Whether we realize this or not, as a country, as a world, as a society as a whole, we are becoming more and more dependent upon renewable energy sources, okay? In fact, one of the more predominant forms of renewable energy right now is wind energy. This is especially true for North America, Asia, and in parts of Europe. In fact, here in the United States alone, nearly 5% of all electricity generated here in the United States in 2015 came from wind-based power sources. Now, that may not sound like a whole lot, but according to the Department of Energy, this number is expected to climb just north of 20% by 2030. Okay? This increased reliance on wind energy will draw the attention of attackers of all shapes and sizes for a number of reasons, okay? And naturally, this raises the question, just how resilient are these control systems to attack, all right? And I find it very interesting that nobody in either the hacker or academic community is really talking about this stuff. Now, I know what you're probably thinking. You're probably thinking to yourselves, well, Jason, isn't this just yet another insecure SCADA ICS system that's vulnerable to attack? And while the answer to that question is most definitely yes, the bigger questions as to what are some of the implications and what are some of the more sinister things that an attacker could do given this kind of access, those types of questions have not been fully answered or even properly reasoned about, in my opinion. We'll talk about that today in this presentation. So again, modern day wind farms, they're operated by a number of interconnected SCADA systems, right? So there's computers and networks in play. What's the worst that could happen? Well, a wind turbine is actually quite similar to a car in terms of, just like a car, a wind turbine has to be serviced and maintained periodically. And just like a car, a wind turbine has to have things like its oil changed, brakes, rotors, gears, and all that inspected and repaired and in some cases replaced in order to prevent bad things from happening, okay? In fact, don't take my word for that. Check out this awesome 10-minute YouTube video whenever you guys get a chance. It basically shows what I'm calling a wind farm engineer's worst nightmare, okay? It literally shows wind turbines failing due to a chain of mechanical failures caused by improper service or maintenance on the turbines, okay? So it literally shows things like wind turbines catching on fire or disintegrating into a million pieces. It's actually quite entertaining to watch. I highly recommend checking it out. So I argue that some of these same types of mechanical failures could also be achieved by targeting insecure control systems. But most importantly, why hack a wind farm? Well, at the end of the day, we want to be able to prevent attackers from turning these peaceful systems into either targets of ransomware or worse, into massive burning wastelands. So what exactly is a wind farm? Well, fundamentally speaking, a wind farm is nothing more than a power plant that converts wind energy into electricity, okay? So we have, it's also important to note that wind is a variable power source, right? So it's not always guaranteed to be there. So we have the wind turbines that are used to harvest this energy, convert it to electricity. Wind turbines will step up the voltage, feed it into substations. The substations step up the voltage yet again, feed this into the power grid, okay? We have a number of SCADA systems that are used to control and manage these turbines and substations, all right? IEC 61400, this is the set of international specifications that define how wind farms are to be designed, operated, maintained, and sort of the abstract communications requirements between the operators and wind turbines in the field. And so like I said, over the past couple of years, me and my research team back home in Tulsa, we've been going all over the country doing holistic security assessments of wind farms and wind turbines from different vendors, different manufacturers, different makes and models, and a lot of them. And so we've looked at everything from the actual physical security of wind turbines to the actual hardware, software, and firmware that run on these automation control systems. And yes, at times we did climb to the very top of these turbines to get a better understanding of how the controllers and field bus protocols and the mechanical systems of a turbine actually work. So if you're a security researcher or a pen tester with any fear of heights, this may not have been a pen test for you to be on. So let's talk about the anatomy of a wind turbine real quick. So we have a tower here, right? At the very bottom of the tower is the base. At the base of the tower, there's a door that opens up that a service technician can walk into to probe or configure an automation control system, okay? It's like an elevator-sized shaft, if you will. Okay, in that same area, there's normally a ladder or an elevator that the technician can take to get to the very top of the tower. That housing on the top of the tower is called a nacelle. And inside of that nacelle contains all of our interesting mechanical components that makes a wind turbine, all right? So these are things like your rotor system, pitch and yaw motors, low and high speed shafts, gearbox, generators, all that fun stuff, okay? These are components that the technician has to regularly check, in some cases repair or replace on a periodic basis, because they will fail at some point. If you're an attacker whose goal is to damage a turbine, these are the types of systems that you're interested in trying to play with or break. All right, and so here is a sort of a 10,000 foot view of the topology of a wind farm, generically speaking. So at the very top, we have a command and control center that's used to manage and control a number of wind farms, okay? And then we have substations at the different field sites. So a substation is actually split into two different systems, all right? We have the transmission control system that's used to collect the electricity produced by the wind turbines, and then it feeds that into the power grid. And then we have the operations control network that's used by operators to sort of monitor, manage, and control turbines in the field. As far as the turbines in the field go, these turbines are sort of all interconnected via fiber optic links, right? Everything is usually IP addressable. There's really no notion of network segmentation between turbines, right? So everything's on a single flat broadcast domain. It's important to note that there is no operational requirement for inter-turbine communication with each other, but the capability is there. Here's a good perspective of the different network protocols in play between the operator and the wind turbine. So the operator can use any number of command and control protocols to talk to control or to probe the turbines in the field. So this is usually a flavor of OPC, a vendor proprietary protocol, or some other IEC specified protocol, okay? At the very base of the tower, there's something called a programmable automation control system, all right? And you can think of a programmable automation control system as a blend between a traditional PC and a PLC, all right? So hardware-wise, this could be anything from, the manufacturers could be designing and rolling their own boards. Alternatively, they could be using off-the-shelf control systems and just rolling their own software onto it. Operating systems-wise, we've seen these guys run everything from Windows, embedded Windows CE, even Windows 95 in some instances, various flavors of Linux, and real-time operating systems of various sorts like VxWorks. They run a number of remote network management services, And then they will talk to other controllers at the top of the turbine and in the cell that are used to interface with the gears, the actuators, and the sensors, okay? And then the protocols between these controllers usually is a common field bus protocol like CAN bus or Modbus. All right, IEC 61400-25, again, this is the part of the specification that defines how operators are to communicate with turbines in the field, abstractly speaking. So it talks about what types of information an operator should be able to pull from a turbine. It also talks about the types of commands that the operator should be able to send to the turbine to put it into a certain context or state, all right? And then what the spec does is it actually maps this functionality back to a handful of protocols listed here, okay? It's important to note that most of these protocols are inherently insecure by themselves. OPC XML-DA, or data access, this was one of the more commonly, the protocols we saw most common during our assessments and research. And this is nothing more than a SOAP-based messaging service. So think XML objects over HTTP, so everything's in the clear by itself. If you look at the spec defines a number of different types of messaging services. So one of the more common types of messaging services that we saw for our testing. So whenever the operator wants to pull a turbine, it will send OPC XML-DA read message requests, and then the turbine will return a list of certain operating parameters and how the turbine is performing. In the event that the operator wants to change a control variable or put the turbine to a certain state, the operator can issue these OPC XML-DA write message requests. All right, here's sort of a generic list of vulnerabilities that we were seeing across the board. Now, this wasn't true for every turbine and every wind farm that we looked at, but these were generally the general themes of the day, if you will, okay? So automation controller-wise, right, we've got these guys that are running legacy operating systems. Everything's running as roots. We have high use of insecure remote network management services, so think Telnet, FTP, SNMP, those sorts of things. In almost every case that we looked at, these automation controllers all are using vendor-provided default CREDs. And oh, by the way, all these CREDs are the same for all the controllers in the wind farm. So if you're able to own one of these guys, it's literally a matter of rule one of them to rule them all. As far as code signing goes, there is no notion of this. There's no notion of code signing on these systems. So we can do things like compile our own binaries and then link against the automation controller provided libraries to interface with different hardware peripherals on the board to do fun stuff. Kind of like I said before, command and control messages in most cases aren't even encrypted. There's really no authentication mechanism for these guys. Wind turbines aren't segmented between each other, which is a huge problem. Physical security-wise, there is no physical security on these guys other than a padlock in most cases. So all that stands between the attacker and the inside of a turbine is a padlock in most cases. There's really no surprises here if you think about it, right? This is the kind of stuff that we would expect from a SCADA or an ICS system, all right? But what kind of interesting effects can we now achieve if we start to chain some of these vulnerabilities together? If we take a deeper dive into the OPC XML-DA spec, it recognizes the fact that this is an insecure protocol, everything's transmitted in the clear. And it says that, it assumes that if you're planning on using this in a production system, that you're going to be using TLS or SSL to encrypt all of your communications. Otherwise, bad things could possibly happen. And here's exactly where it calls this out, all right? In every case that we looked at that was using this protocol for command and control, no one's doing this. No one's encrypting these messages or these protocols. If you look a little bit further in the spec, it also says something about, we recommend that you disable the ability for just anybody to send these arbitrary write message requests to the OPC server. So it recommends having some sort of authentication mechanism or putting the OPC server into read-only mode. Here's a list of items that are usually pulled from the operator and sent back to his HMI screen. So things like wind speed, brake status, ambient temperatures, controller operating statuses, those sorts of things. And here's where things get interesting. So here are the types of commands that the operator can send to turbines in the field to get them to do things, all right? And this will vary from vendor to vendor, but we can generally do things like changing the maximum power generation output of a turbine. We can do things like controlling the operating state of a turbine, so being able to put it into, turn the turbine off or turn it on or put it into an idle state, okay? Another interesting state that the turbine can be in is something called the emergency shutdown mode, all right? And what emergency shutdown mode is basically when the automation control system or the operator has detected conditions, external conditions, that could be damaging to the turbine if it continues to operate. So things like high gusts of wind, maybe a tornado is imminent, those sorts of things. And what the system will do is, in the event that it wishes to put the turbine into an emergency shutdown state, it will initiate something called a hard stop, all right? And these hard stops, what happens is it will actually, the rotor, it's operating, the rotor will actually flare out the blades and then lock up the mechanical brake on the turbine to bring the turbine to a halting stop as soon as possible. And it is not a graceful shutdown, believe me. So when this happens though, we actually can induce excessive wear and tear on critical mechanical components inside of the nacelle. So the gears in the gearbox and that sort of thing, even the physical integrity of the rotor and the tower structure in some cases. And there have been plenty of mechanical engineering research that backs up those claims, by the way. Also, if you're ever doing this type of testing with a group of wind farm engineers and you try to force a turbine to hard stop more than 0 times, they tend to get very grumpy with you. All right, so you're probably asking yourselves, this sounds great and all, but how am I supposed to get physical access to a wind farm control system network? Well, there's a couple of ways this can be done. The easiest way of doing this is to literally walk up to a turbine out in the middle of a field somewhere and either pick or bust the lock. Then once you're on the inside, there's usually a network switch that you can just plug into an open port. And again, these guys, in every case we looked at, no one's using port security or anything like that. Assign yourself a static IP address and boom, you're on the network, okay? During our testing, we would use Raspberry Pis outfitted with Wi-Fi modules and do all of our testing on the outside of the turbine. All right, let's talk about some of the network-based attack tools that we've developed. So Windshark is a Python-based tool that we use to hijack control of wind turbines or damage them, okay? And so the way it works is Windshark will actually scan the network for the IP addresses of automation control systems running certain OPC servers or certain control services that we care about. It will then return the list of IP addresses to the attacker. The attacker can then choose which IPs or which set of IPs to target. At this point, he can also initiate, which commands that he wants to send to the turbine. So being able to put a turbine, turn it off or turn off all turbines, okay? And so that's how we're able to hijack control these turbines, is by spoofing some of those OPC messages, those write request messages that I talked about. Now, this doesn't do anything to hide what we're doing because the operator can still pull those automation control systems and see what we're doing. So we still have that to deal with. As far as trying to damage the turbines, here's what we can do. Windshark has an awesome mode called the hard stop of death attack mode. And the way this works is it will actually force certain turbines to hard stop, and then it will wait for them to recover from that hard stop, and then hard stop them again. And it will repeat this process over and over again until either we're removed from the network or the program is halted, its execution has been halted. So, and by doing this, we're increasing the wear and tear on those crucial mechanical components, meaning we are slowly damaging the turbine. Wind Poison is the next step up from this. Wind Poison is a man-in-the-middle tool that we've put on a Raspberry Pi that will use the old ARP cache poisoning trick to ARP cache poison all the controllers of the turbines and then the operator's workstation. And then after this, we can do stuff like, man-in-the-middling operator messages, doing things like dropping those request messages, and then falsifying those responses back to the operator and lying about the current operating state of the turbines in the field. So in the event that we've shut down turbines that are supposed to be operating, or that we're forcing certain turbines to go through the hard stop of death attack, we can hide what we're doing and just lie back to the operator. And we can get away with this because, again, with that specific protocol, it's over HTTP and everything's in the clear. There's no authentication or anything like that. So these network attack tools were designed to target the IEC 61400-25 suite of protocols and network services. We had to do some light command and control protocol reverse engineering to figure out what some of these values were to put certain vendor turbines in a certain context and state. We put everything on a Raspberry Pi, tied everything together with Python, had some bash scripts. We used the Scapy and Nmap Python libraries for packet manipulation and port scanning. And then we did some IP tables foo for dropping and forwarding packets across interfaces. Let's take this to a step further with Windworm. So Windworm is a proof of concept that we developed in the lab designed to take advantage of the insecure and the insecure configuration of automation controllers that we were seeing. So we take advantage of the fact that these automation controllers all have the same credentials. We're assuming we know what those credentials are. And we also take advantage of the fact that these guys are running FTP and Telnet. And so we use FTP to propagate ourselves from one automation controller to the next, and then we use Telnet to invoke ourselves. And we repeat this process over and over again until we have code execution on all the automation controllers in the wind farm, okay? And again, so we're able to interface with the field bus controllers by linking against the automation controller library to allow us to do fun stuff with that. And once we have code execution on the automation controller, we can do things like being able to inject our own messages to talk to other controllers, more interesting controllers in the turbine. So during our assessments, one of the more prevalent protocols that we looked at was a protocol called CAN-open. CAN-open is a very commonly used industrial automation control protocol, okay? And so the way it works is every node in a CAN-open network has something called an object dictionary. And this is very similar to like Modbus registers and Modbus. And so if you know, and these object dictionaries contain process configuration, process data and configuration settings for a controller. And so if you know the layout and the structure of this object dictionary, you can actually do things to modify those process control variables that you're interested in, all right? And so the way this works with CAN-open, the spec defines something called an electronic data sheet. And you can actually use this electronic data sheet, and it will tell you the mappings and the layout of a certain object dictionary of a controller. So it will actually give you the literal name of an element inside the object dictionary, the data type, what index is located at, subindex, and all that, okay? Once we know where these interesting elements are in these object dictionaries, we can simply inject our own CAN-open share data object message to actually modify critical values that we care about that are vendor defined in that object dictionary, okay? So doing things like increasing RPM limits or thresholds, or things like that. All right, let's take this yet a step further. What if we wanted to ransomware a wind farm? How exactly would this work? And when I say ransomware wind farm, I'm not talking about encrypting anything. I'm talking about paralyzing wind farm operations in such a way that they're no longer able to produce electricity, unless maybe a ransom is paid with Bitcoin. But how exactly would this work? This is exactly how somebody would go about ransomwaring a wind farm for Bitcoin. And the idea here is that the attacker would have to get access, physical access to a single wind turbine. The attacker would then introduce propagating malware, very similar to the windworm that we just described. The malware would then place the turbine into a paralyzing state, meaning that it would just disable, it would shut down the turbine. Then that malware would disable all remote network management services. It would then unload the serial driver used for local console access, and then it would start up its own TCP network service that would just sit there waiting for a ransomware key. At this point, you, the attacker, have now owned the entire wind farm. And what you would do then is you would send a ransom note to the electric utility over email saying, hey, congratulations, I've just now owned your wind farm. If you'd like to have your wind turbine assets back in a timely manner, please send $10,000 in Bitcoin to this address. Let's say the company complies with that and pays the ransom. They would receive their key back, and they can use this key to unlock their wind farm to resume operations as normal. However, if the electric utility or the company decides not to comply, and they're like, nah, man, we're going to figure this out on our own. We're not going to work with the attacker. What that malware could do, it could have some logic built into it in such a way that if that ransomware key has not been received on every, within a half an hour or on the hour, it could actually force the turbine to do the hard stop of death attack over and over and over again, maybe once an hour or so, until that ransom is paid. So now not only do we have the problem of the electric utility losing out on money because because their wind turbines aren't able to produce electricity, but we also have this problem where the attacker is able to cause damage to turbines. Very interesting. So what would be the financial impact, though, due to wind farm downtime? All right. Well, if we take for an example of a 250 megawatt wind farm, for instance, that's been infected with this type of ransomware, and we assume that the national average for electricity is 12 cents per kilowatt hour, per hour of downtime, we're talking, and we assume that the capacity factor on the low end is 35%, and on the high end is 100%. For every hour of downtime, that electric utility is losing out on anywhere from $10,000 to $30,000 per hour in this case. Okay, that adds up really quickly. In fact, just over the course of 48 hours, we're talking about lost revenues anywhere from $500,000 to just under $1.5 million. That's a lot of money, folks. So what would you do? How would you recover from something like this? Well, there's different perspectives on this depending on who you are, if you're the operator or the vendor in this case. You could maybe re-image the automation controllers. In some cases, it's as simple as popping out the multimedia card where the file system resides on, so compact flash or SD card, and going that route. In other cases, it's not so trivial because the file system resides on a flash chip that's soldered onto the actual control board. So good luck trying to do that in a timely manner. Additionally, you could replace the hardware on all of your wind turbines. Again, this is going to take a lot of time and going to cost you a lot of money. And then assuming you're able to remediate the infection, how confident are you that the infection's actually gone and that won't reappear again in the future? In the meantime, while you're trying to figure this stuff out, you, the operator, are losing out on your ability to generate electricity, which means you are losing money. All right, so in conclusion, wind farm control networks are extremely susceptible to attack. Again, this is just the tip of the iceberg based on some of the research that we've done. My advice to any kind of electric utilities out there that have wind farm assets is to be proactive. Don't wait on vendors to provide you with security. Verify vendors' claims. If they're promising you things like encrypted command and control or network segmentation, verify those claims. And then lastly, retrofit security is needed. If you had something in place where you could maybe VPN tunnel all traffic over an encrypted tunnel between turbines and the substation, you would be able to prevent all the attacks I just described right here, okay? So in the event, in that case, if you had one turbine that was compromised, that one turbine couldn't bring down all of your wind turbine assets for your wind farm, okay? All right, with that, I'm out of time. So if you have any questions, comments, or even crazy ideas, I'll be around. Come find me, let's talk. Otherwise, thank you all very much.